Okay guys, in our last video we kind of introed what we think about mathematical sequences as being these list of numbers that occur in order, or at least we can define it mathematically as just a function whose inputs, which represent term position, are the set of positive integers and whose outputs reflect the term value. If you're given a term rule, which is kind of nice, those are great because we can write out the terms of a sequence or find the values of a term in a given position. So if you know the position, I can give you the term value. Fact is though, for a lot of the sequences that we look at, like these two that you see here, we're going to have the actual sequence, but what we're going to be curious about is we don't have a rule, so we kind of want to write a rule that would help us find the value of the nth term in a sequence. So the very first thing I want to kind of indicate here is this. Given a sequence of terms here, so your first term value, your second term value, your third term value, all the way out to maybe the nth term value and beyond, we tend to like to write a rule for the nth term. And what a rule for the nth term does is it gives us the value of any term as long as we know what position it's in, or the nth position. So we're going to make sure that we write this out here. What do we mean by the nth term rule? It is a rule that gives the value of the term in the nth position. Basically meaning that as long as you know the position, then we know what we can plug into our function or our rule in order to find the value of that term. So our job is going to be to come up with an nth term rule here. So looking at this, it says describe the pattern, then write the value of the next term. Then write a rule for the nth term of the sequences here. We're going to start with this first sequence. So what I'm going to share with you in this video is just kind of a best practice. But one of the best practices you can do is just kind of simply get used to this idea of what is it that I could verbalize or say is going on with our pattern here. And so some things we tend to look at. We tend to look at things like how they grow. I notice that this is all negative from term to term here. It's not oscillating from positive to negative to positive to negative. So some things that I might write here, you know, in terms of my description, we can go ahead and write one down. We can say every term is negative. Okay. What are some other things that we maybe notice about this first sequence here? Well, I happen to notice that 1 and 8 and 27, maybe not 64, but those are perfect cubes. That is to say, like 1 is a perfect cube of 1, 8 is a perfect cube of 2, 27 is a perfect cube of 3, and if I'm describing this pattern correctly, 64, as a matter of fact, is a perfect cube of 4. So we can say that the numbers on the list are perfect cubes. Okay, so we wanted to describe this here. As far as any other patterns that I see occurring here, well, sometimes we talk about how much it increases or decreases by. We simply could write from -1 down to -8. It went down by 7. You know, we could say maybe it went down by 7. And then from -8 to -27 here, it goes down by, 19. And then from -27 to -64, I think it goes down by like 33. I'm not really seeing a pattern here. So with respect to what it's going up or down by, that's not very helpful here. All I notice is that every term is negative and the numbers on the list are perfect cubes. So we're going to go on to the next thing here, which is kind of after you've described what's going on, could you represent this in maybe a table? And the reason why is because we really want to look at this as a function. So we're going to say that our first term, our second term, our third term, and our fourth term are our n values here. And we got outputs of -1, -8, -27, and -64. So the idea is going to be this. If we want to write a rule, first things first, we're going to write that our rule is some a sub n, or you could write it as f of n. But the real question is this. What is it that we're doing to our n values here that's getting us over to our a sub n values here? So you might argue that what we're really doing is cubing these input values, and I would actually agree with you. If we take 1 cubed, or 2 cubed, or 3 cubed, or 4 cubed, we're going to get these values over here. The only thing that we need to be careful of is that I also noticed that the values on the right were negative. And so in order to write a rule here, I think what I would indicate is that I'm going to take my input value and I'm going to cube it, but the other thing I want to make sure is that it's negative here. So with respect to what a rule would be here, I could say that our rule would be, I'll draw an arrow here, a sub n is equal to negative n cubed. And I'm going to put a box around this. Same thing down here, we're going to say f of n is equal to negative n cubed. And does this work? The thing is, once you've written a rule, this is kind of like a guess, it's like a guess. And the thing is, we need to make sure it works. So what we're going to do is we're going to go plug in a few of these inputs from our table and make sure our rule works here. If I were to use the rule that I've written here and plug in a 1, then I would get negative 1 cubed, which is negative positive 1. If I were to plug in, say, my 4 here, f of 4, I would get negative 4 cubed, which is negative positive 64. We can see that this rule is working. So with respect to writing rules, we always describe, represent it in a table, and then try to determine what is it that we're doing to n values to get our a sub n values, or f of n values, and then test the rule. Okay, so we're going to try this again for letter B here, see if we can't come up with a rule. I'll kind of drag this down here. First thing we want to do is just basically describe it. So in terms of description here, I notice that not all the numbers are positive. One of them is a neutral number here, and then it's going up by 2, up by 4, up by 6, so plus 2, plus 4, plus 6 here in terms of this change here. So if I had to describe this, how might I describe this in words here? Description. We say that the terms are always increasing. And how about terms always increase by 2 more than each previous term increase. Now, I happen to know, and that's because I look at a lot of quadratic things a lot of time, that quadratic things or parabolas here behave a lot like this, where you're speeding up, okay, kind of like gravity behaves this way. So the question is, how the heck do you write a rule for something like this? Hey, you know, it might be quadratic, but you're not going to see that at first. So the thing we have to do is, again, provide a table. Let's try this here. If we were to provide a table for our terms, this time I'm going to use n, and why not we'll use like b sub n here. Suppose I go 1, 2, 3, 4 terms, and we had a values of 0, 2, 6, and 12. So the question is, what is it that we're doing to the n values to get the value of b sub n here? And this one's a little bit trickier, but as you start to play around with these, you start to see patterns like, maybe what if I took 1 times 2, what would I get? I would get this 2 right here. Or maybe if I took the 2 times the 3, I would get this 6 right here. Or maybe if I took the 3 times the 4, I would get this 12 right here. So for any given value right here, you can see that what we're doing is we're taking its n value and we're kind of multiplying it by the n value that occurs right behind it. So with respect to our rule, how could we put this in words? We could say, well, our sequence nth term then is always going to be equal to whatever position that it's in times the position right behind it, which is 1 less than n here. And with respect to this rule, we just want to make sure that it works here. What if I wanted to find the value of the 5th term here, b sub 5? Well, according to this, it would be 5 is our n value, times 5 minus 1, which in this case would be 5 times 4, which is 20. And looking at this, that would kind of carry out the same kind of scheme we've seen before. 5 times 4 is equal to this 20 right here. And so it does indeed work, and this would be our rule right here. So again, I do want to throw this out there. It's not always the easiest thing to write rules, just because you got to kind of put your critical thinking cap on. But there are some things we can do to make it consistent every time. Give a verbal description of it, write it in a table, and start to think about what is it that we're doing to our inputs to get us over to our outputs. And then once you get a rule written, you think you feel good about it, make sure that you test your rule. Cheers.